Charter. We don't just cover one institution, we cover at the moment 7 institutions around Ireland itself, in Dublin, Cork and in Limerick. Currently we cover areas from wireless to optical networking, antennas, optimization, photonics, thermal, a fairly wide range of telecommunications topics. In the coming year, CTVR will be expanding, adding a number of new institutions, including Waterford, and broadening the range of topics which we address in our research. We work closely with a wide number of companies, large and small, across the country of Ireland, ranging from companies like Dell, Analog Devices, Xilinx, Alcatel-Lucent, down to more recent startups like Software Radio Systems and SocoWin. Software Radio Systems was a company that was created along with the open sourcing of IRIS. So it's a company created to manage the software and to push it forward. So that's just a very introduction to who I am and where I come from. The next part of the presentation is looking at IRIS itself. So I'm going to start off just with an overview of IRIS, take a quick look at the architecture, look at how we get started using IRIS, and then some more detailed topics like controls. And I want to look at OFDM as a case study, how you implement OFDM within IRIS. It's a more practical look at a key technology for most wireless applications. And then just a discussion of a couple of interesting applications that have come up in the last year. So starting with an overview of IRIS. What is IRIS? IRIS is an architecture for building software radios. It's the scaffolding you can use to build a radio in software. So if you start out and you decide I want to build a radio in software, you can start from scratch, absolutely, and build it up yourself. The reason why you might use a framework like IRIS is because it gives you a bit of a head start. It gives you some of the building blocks that you know you're going to need. So it handles things like threads, concurrency. It gives you a number of existing blocks that you're going to need, like file I/O, sockets, logging, hardware interfaces. If you want to talk to an RF front end, blocks may already exist to do that. There are graphical utilities that you can use to display your signals, to debug any issues you might come across. And then of course you have various blocks which do software radio DSP. So you'll have modulators, demodulators, filters, scramblers, and so on and so forth. So IRIS is reconfigurable. Reconfiguration is at the heart of the design of IRIS. It was designed from the ground up to be reconfigurable. So if you're going to build a radio in software, why build it in software in the first place? It's because of the flexibility you get from doing it in software. And reconfiguration is at the heart of that flexibility. So every block within IRIS exposes parameters which can be changed at runtime. That means that you can change how your radio operates while it's operating. And there are tools and mechanisms to handle that type of runtime reconfiguration. And of course it's a component-based design, which gives you a very flexible way to build and to reconfigure your radios. So it's primarily designed for general purpose processors, for the generic processors you find in your laptop and your PC. But we have used it with more exotic processors, FPGAs, GPUs, the cell broadband engine that was in the PS3, these types of things. So it's not limited to GPPs, but that's its primary focus. So I say it's a component-based architecture. So when you build a radio, you build it by combining various different types of components into a radio flow. So you might use pre-existing components, and you might build your own components that don't already exist and which you need. So these get linked together at runtime to create your radio. We use an XML configuration file to specify what components go into a radio and what parameter values are used for those components initially. Each component is built as a dynamic library. IRIS itself, the code base is split into two, into the core and the modules. So the core is responsible for looking at the XML configuration file, finding out what modules or components are needed for the radio, finding those dynamic libraries associated with those modules, loading them up, linking them together, and running the radio. So you have your core and you have repositories of modules which are built as dynamic libraries, and you might have multiple repositories which you can draw from. So IRIS is written in C++. We use all the usual C++ safe pointers, containers, exception-based error handling. So it's quite fast, but it's relatively forgiving as a language to write in. The code base for IRIS is portable, so runs on Linux, Windows, whatever. We use CMake as the build system. You might have come across that before. And we use portable Boost C++ libraries for things like threading, for file and socket I/O and so on. And very importantly, it's extensible. So you can always add new modules to extend the capabilities of IRIS. But along with that, the core is designed to be extensible as well. So there's a concept of an engine within the core, and I'll talk a little bit about that more later. And most importantly, it's open source under LGPL v3. It was released under open source in January of last year. It had been in development for about 5 or 6 years before then. And it took a while to get it open sourced. If you're working within a university and you decide to embark on a project and you want it to be open source, make sure you open source at the start and not at the end. Speaking from experience. So what can I do with IRIS? I'll just run through a couple of the types of systems that we've built in the past. The first one, this is a dynamic spectrum access scenario. So with dynamic spectrum access, you're automatically determining the carrier frequency and the bandwidth that you're going to use for your radios at runtime. So that's fine if you have a base station boots up, has a look and sees what frequencies are available, chooses a carrier frequency and a bandwidth. If you have subscriber stations or receivers that want to operate with that base station, how do they determine what those carrier frequencies and bandwidths, what those physical layer parameters are? The approach we used was this idea of a physical layer watermark where you embed a signature into the transmitted signal. It's easy to generate, it's also easy to detect at the very, very lowest layers of the physical layer. And using those signatures, you can find out these parameters. So you can find out what the carrier frequency is and what the bandwidth is. So we've done various demonstrations using streaming audio, streaming video over OFDM, embedding a watermark into the physical waveform, and then at the receiver using that watermark to tell us what the carrier frequency and the bandwidth was. So the demonstrations typically consist of, dynamically changing the carrier frequency and the bandwidth at random stages, and having the receiver automatically detect that and reconfigure itself to maintain a communications link. So you have continuous audio or video streaming or whatever. Spectrum Wars is a more recent demonstration. Again, this is dynamic spectrum access, but this was a little more interesting as it's an interactive game for 4 players. So the idea is that you have 2 teams. Each team consists of a transmitter and a receiver. Each player has a software radio that they control. There's a graphical interface for changing the carrier frequency, the bandwidth, the gain. And the objective of the game for each team is to create a link between the transmitter and the receiver to transmit data from A to B. As data is transmitted, on a main display you have scoring bars, and the first team to transfer a set number of packets is the winner. While the game is going on, you have a large display showing what's going on within the band of interest. So you have the power spectrum showing you which signals are being transmitted, their carrier frequency and bandwidth, and then you've got indicators to show where the receivers are and what the instantaneous receiver's carrier frequency and bandwidth is. So it's a very intuitive way of understanding some of the key issues in dynamic spectrum access, such as link rendezvous and link maintenance in the presence of interference. There's also primary users who transmit within that spectrum band just to make things more interesting. And of course, this particular demonstration illustrates some of the graphical interfaces that you can develop using IRIS, and which you can use to then control your radio and display what's going on with your radios. And the last experiment was an experiment developed last year to demonstrate handover between heterogeneous networks. So this consisted of a radio on a train, and you might have heard of snakes on a plane. This is radio on a train, where you have handover as the train moves between hotspots. You get this handover between heterogeneous networks. The last example, this is quite interesting. It was a COST short-term scientific mission. A student called Jacek Kabilda came. He had 2 weeks to do a particular job. He had no previous experience of IRIS, And he built a quite interesting dynamic spectrum access demo. So this kind of shows the quick learning curve that's associated with IRIS. So he built a system with a base station and a couple of mobile stations. And he used a fixed frequency control channel to avoid creating interference with the primary user and to maintain a data link between the base station and the mobile stations. There's a blog write-up about it there if you want to find out more. But this was very interesting from the point of view of having a short amount of time to try and do something quite interesting and achieving that very quickly. So that's a quick overview of what IRIS is. I'll look now a little bit at the architecture and some of the details of IRIS itself. So as I said, it's a GPP-based software radio architecture, and the fundamental block is the component. So in a most basic configuration, you'll have a source component, a sink component, and you'll have some processing between them. And you'll have a flow of data from the source to the sink through those processing components, like this. And we use an XML document to describe that radio structure. So this is an example XML document. You define your software radio, you give it a name. Here we're just using one engine. I'll talk a little bit more about engines later on. This is a physical engine. So you have 4 components. You have a file reader, an OFDM modulator, a signal scaler, and a USRP transmitter. Within each component you can define parameters. So for example, if we're reading from a file, you specify the name of that file. And you can define a port, so our file reader just has one output port. And then at the bottom we specify the links, which outputs are connected to which inputs. So as you can see, this is quite simply a set of 4 components coming from a file reader, OFDM modulating the data, scaling it, and transmitting it via USRP. So this is quite a simple OFDM transmitter. So you can have a simple chain in a sequential order like that, but of course the data that's passed through it is a data set. It consists of a vector of data samples, but there's also metadata, for example, timestamps and sample rates. So for example, if you are receiving from a RF front end, you might want to know what the sample rate of the blocks of data you were getting are, and you might want a timestamp associated with the first sample in that block. So as well as a simple sequential chain, you can have blocks of multiple inputs, multiple outputs to build up more complex radios. So I mentioned engines already. This is within the core of IRIS. An engine is an environment within which one or more components operates. It defines its own data flow mechanism, reconfiguration mechanisms, runs one or more of its own threads, and provides a clean interface for the IRIS system. So basically an engine executes a section of a flow graph of a radio, but it's completely up to the engine how that's done. And when I say that IRIS is extensible, there are pre-existing engines, but you're free to write your own engines as well. So if you want to implement your own reconfiguration mechanisms, implement your own data flow mechanisms, you're free to do so by re-implementing engines. Currently, there are 2 types. There's the physical layer engine and the stack engine. Physical engine is designed for maximum flexibility. There's one thread per engine. It's data-driven execution. You can have one or more components per engine, multiple component inputs and outputs. Unidirectional data flow, so for a physical layer you're going to have data flowing from source to a sink, one direction. There's no fixed relationship between inputs and outputs of a component, so you have these flexible block sizes. So the physical layer engine is quite an easy engine to work with initially. There are very few restrictions on what you can do using it. For example, if you're going to write a OFDM receiver to operate with the transmitter that we discussed already, you'd have a USRP receiver. You can put in a signal analyzer there if you want to do some spectrum sensing. If you demodulate and you simply write the file. The stack engine, on the other hand, has a network stack architecture, so the components are the layers within that stack. Each component runs its own thread. You have bidirectional data flow up and down the stack. So for example, if you want to write a MAC layer or a routing layer, you would do it within the stack engine. Putting these 2 engines together, you can come up with quite complex transceivers. So for example, here we combine 2 physical layer engines, one for our transmit chain, one for our receive chain, both using OFDM. We've got a signal analyzer in there, and we've got our stack engine providing MAC layer, routing, security, whatever else we need. So drilling down into a little bit more detail, I'll just take a look. There's going to be some code here. I'm not sure if you're going to be able to read this at the back, so I'll go through it quite quickly. to define your component, you're just using a template of a specific set of functions which have to be defined. You've got constructor, you're going to register a couple of ports, you're going to calculate the output types, you've got initialize and process. So the process function is where the work gets done for your component. In the constructor, you can simply register a parameter. So here it's just an example parameter that can be changed at runtime. And you register ports, so you say what your ports are, what data types they're going to be able to handle, and then calculate output types. When your component loads, the system will tell your component, okay, this is the data type on your input, tell me what your data type is going to be on your output. And then you've got process. So this example is simply taking a data set from the input and copying it directly to the output. So you have get the input data set, you use that input data set, and then you release input data set. In the same way you get output data set, you write to it, and at the end you release it. So it's fairly straightforward. Stack component, very similar. A couple of functions you have to implement: initialize, start, stop. You have process message from above and process message from below. So you can register parameters, you can register your ports, and then you've got send up and send down to get that bidirectional data flow. So the actual architecture of the core itself, you have component and controller repositories. So I'll tell you a little bit more about controllers later on. Those are a different type of module within IRIS. You have engines, which use a component manager to load up the components it needs, link them together, and manage their lifecycle. You've got the engine manager, which looks after all of the engines running within the radio. You've got the system. You've got a fairly basic C interface. So IRIS is written as a library itself. So when I talk about IRIS being extensible, this is another way in which it's extensible. So the default launcher for IRIS is a console interface, but that just sits on top of a basic C interface to the IRIS library. So it's very easy to write your own IRIS GUI if you want to sit that on top of the library again. You've got an XML parser to manage your configuration files and a reconfiguration manager. So at runtime, you can quite easily change values within the XML file, trigger IRIS to reread the file, see what the differences are, and execute those reconfigurations. So that's just one way you can reconfigure the radio at runtime. Obviously, there are more complex ways of doing it. So getting started, just a couple of links. The top one is where the code is. It's all on GitHub. There is a Redmine project page with issue trackers, wikis, so on. There are various mailing lists, and there's a blog which contains some more detail on how to use IRIS and how to get up and running with your first radios. So far we've discussed how we create a radio and how we reconfigure it manually using the XML files. But what's of more interest is how we reconfigure a radio dynamically, so at runtime. And that's where controllers come in. So looking again at our receiver example, where you've got our receiving from the USRP hardware, signal analyzer, OFDM demodulator, file writer, we can expose parameters within components and we can reconfigure them at runtime. We can use events. So in addition to specifying parameters, each component can specify an event. So it says, okay, if something happens, I'm going to trigger this event. It goes into the IRIS system. It says, hey, this has happened. So for example, if we have a signal analyzer that's doing energy detection, if the energy crosses a threshold, it can then trigger an event and tell the system, hey, something's happened. You need to do something about it. And that's where the controller comes in. The controller is the guy within the system that listens for those events and changes the radio in response. So for example here, if we had a flexible OFDM waveform, we were changing the number of subcarriers, for example, our signal analyzer could be telling us how many carriers are being used. So it's determining that with a very low file layer. Each time it changes, it triggers an event and tells the controller, hey, something's changed here. The controller responds by reconfiguring our OFDM demodulator. So you get that flexibility and that reconfiguration to enable a continuous flow and to maintain the link. So in a more complex transceiver, you can have a single controller that's handling a whole number of these different interactions between the individual components. So that's the overview of IRIS, how you build a radio, how you manage reconfiguration within the radio. The next thing I want to take a look at is a case study of OFDM. So looking at what OFDM is, what the limitations are, and how you implement it within a software radio. So I'm sure you're all familiar with the various standards that are implemented with OFDM. You've got LTE, Wi-Fi, Wimax, DSL, digital radio, so on and so forth. So where did OFDM come from? Why was it implemented? What are the strong points of it? Within single carrier systems, looking at a time and a frequency representation, as the demand for faster rates increases the rate at which our signals our symbols are changing and the rate at which we're transmitting symbols, the frequency, the bandwidth of our signal increases together with that. As we move to broadband systems, you start running into a few problems if you're going to use single carrier. So the first one of these is multipath propagation. If you've got a transmitter and a receiver, you don't get a single trajectory from the transmitter to receiver, you get echoes and reflections of all the obstacles between the two. So that multipath propagation will result in frequency selective fading. So you have your strong signal that you're interested in, but you get all these echoes and reflections that come with it. And that gives you frequency selective fading, which is going to corrupt your signal. You also have narrowband interference. So if you have a narrowband interferer, that's going to corrupt your single carrier signal and cause various different problems for you. So a couple of ways of getting around that. Instead of having a single carrier system, why not have a multi-carrier system? So instead of one broadband signal, have multiple narrowband signals and transmit them in parallel, side by side. So if you have multipath propagation, instead of giving us this frequency selective fading, that frequency selective fading then is like flat fading on individual carriers, much easier to correct and rectify. Our narrowband interference, instead of corrupting our entire signal, might now just knock out one or two of our subcarriers, and we might still be able to retain some of the data from the original subcarriers. So a very efficient way of implementing this was orthogonal frequency division multiplexing. It's the closest we can pack parallel subcarriers, where the peak of each subcarrier is at the trough of the neighboring subcarriers. And the fast Fourier transform is a very efficient way of achieving this. So if we have our frequency selective fading, we can correct each individual subcarrier. That equalizer is just a one-tap equalizer. It's a hell of a lot easier to implement than for a single carrier system. So we want to use simple multiplication of the frequency domain to equalize that channel. So with convolution in the time domain corresponds to multiplication in the frequency domain. That's fine for a continuous time Fourier transform. The fact doesn't hold for discrete time Fourier transform. So in a discrete time Fourier transform, instead of regular convolution, we get circular convolution. So we need circular convolution in the time domain to get that multiplicative effect in the frequency domain. So we want circular convolution, we don't want regular convolution. The problem is that the real channel does regular convolution. So within OFDM we use this trick to make it look like circular convolution, where we use a cyclic prefix. So we take our OFDM symbol, we take the last part of it and we copy it to the front of our symbol. That gives us the appearance of circular convolution and allows us to use simple multiplication in the frequency domain to do our equalization. So we take each symbol, we take the last part of the symbol, we copy it to the front and we get that cyclic prefix. So this eliminates intersymbol interference and it turns linear convolution into circular convolution. So looking at intersymbol interference, if you've got a single carrier system with our individual symbols, we have multipath propagation, we've got these echoes and reflections and delays coming in. So each symbol bleeds into the following symbol. This is our intersymbol interference, which is going to cause us a lot of problems. With OFDM, firstly the time domain symbol durations are much longer, which is going to help us. And we also have this cyclic prefix at the start of our symbol. So we get these reflections, it means that our symbol bleeds into the next one. But it doesn't matter too much because it bleeds into that cyclic prefix. And that cyclic prefix is redundant data, so it doesn't affect our core data, which we can still extract. And because we have this circular convolution, all of this bleeding and all of these reflections actually combine to increase the power of our received signal. So they tend not to interfere so much. So OFDM isn't perfect, it has a couple of drawbacks. An obvious one is the high peak to average power ratio. So if you look at the time domain view of an OFDM stream, you'll see that there are very, very high peaks compared to the average power. If anybody's looked at LTE, so the most recent standard, so comparing Wimax with LTE, can anyone tell me what a fundamental difference between Wimax and LTE is? So in the system architecture for Wimax and LTE, any major differences? So the one biggest difference between the two is that Wimax uses OFDM, plain OFDM in the downlink and the uplink. LTE decided not to do that. LTE uses plain OFDM in the downlink, and they use single carrier FDMA in the uplink. So different modulation scheme. The reason they did that is because of this high peak to average power ratio. So if you use plain OFDM in the uplink where you've got a handset with limited battery life, you're going to have to run your power amplifier at quite a low level in order to cope with all these very, very high peaks. So that means that your battery life is going to be abysmal. So with LTE, they said, rather than using plain OFDM, we're going to use a single carrier frequency division multiplexing, which removes this problem of high PAPR and gives you much better power efficiency. So it means that your handset for LTE should last much longer on the same battery than it will for Wimax. So that's just one way that this issue of high PAPR was avoided. The second major issue with OFDM is that your out-of-band roll-off is quite slow. So if you look at the power spectrum for Wimax, or if you look at the spectrum bands, the masks for Wimax, they're quite lenient, so they give you a lot of time to roll off. And for systems like LTE, you don't have that sort of flexible roll off, these high sideband levels. So instead of using plain OFDM, you have to come up with ways to reduce those side lobes and allow you to put systems closer together. It's one of the reasons, actually, you'll come across some people talking about LTE for the ISM bands. One of the reasons they talk about LTE for the ISM bands is that LTE plays much nicer with its neighbors than Wimax does. So if you try and put a system beside a Wimax signal, you're going to get hit by that out-of-band emissions. If you do that with LTE, it has reduced side lobes, so they play a little bit nicer with their neighbors. So there's a lot of research going into PAPR reduction through clipping, signal scrambling, and so on. And then spectral shaping is a big research area where you do symbol shaping, you can use cancellation carriers, and so on. So having looked at the background of OFDM, how do we go about creating an OFDM radio using IRIS? So for the modulator basically looks like this. You get a stream of data coming in, you're going to scramble it, whiten it, you're going to map the symbol onto a constellation, BPSK, QPSK, 16 QAM, so on. You're going to take those symbols and put them onto subcarriers, you're going to put in pilots, you're going to do an inverse Fourier transform. So that takes, you build your signal in the frequency domain, you do your inverse Fourier transform, get into the time domain, get your symbol, you add your cyclic prefix, and then you transmit it. That's basically what your modulator looks like. If you're going to create a frame, your frame might look like this, where you've got a preamble symbol for synchronization, a header symbol, a couple of data symbols, and a frame guard at the end, possibly. So, with the transmit preamble, one of the things we want is a repeated sequence. So, using a repeated sequence, it makes it possible for the receiver to do your time and frequency synchronization. If you're going to do an inverse Fourier transform, one way to get a repeated sequence is, instead of putting data on every subcarrier, put data on every second subcarrier. So this is a frequency domain representation. You've got your real, imaginary, magnitude, and phase. So if you look at the magnitude, this is our centered frequency here, and you can see that we've got data on every second subcarrier, not on every subcarrier. Moving into the time domain, that gives us a repeated sequence. So if you look closely here, you can see that the first half of the symbol here is exactly the same as the second half. So you might have to look closely, but you'll see features like, for example, this peak here, the same as this peak here. So you get this half symbol repetition. So on the OFDM demodulator, what does that look like? The various steps are, you've got your frame detection, your frequency offset correction, preamble extraction and equalizer generation, your Fourier transform, get into the frequency domain. There you do your one-tap equalization, you pull the data off the subcarriers, you demap the symbols, and then you de-whiten the data. So it's basically the reverse of our modulator. So I was talking about the preamble and how you have this repeated sequence for the preamble. This is the algorithm used for Moose and Spittle and Cox. You might have come across it before. So the way that these algorithms work is you're getting a sequence of incoming data. Within this stream, you know that there's a repeated sequence. So you're going to use two windows and you're going to correlate them. So you're just going to slide them along and you're going to correlate the first window with the second window. And this is the combination of the two, and this is the output of your correlator. So as you step through, you start to see, hang on, my first window is starting to correlate a little bit with my second window. The output of your correlator starts increasing. When they match, your correlator reaches a peak, and then that's how you get your frame detection. You know at that point I've got a frame that's coming. For a real signal, with OFDM, I told you there's a cyclic prefix. You don't get a clean peak. You get this kind of a plateau. So you have to deal with that plateau to estimate your simple timing. So you
Excuse
can...
me.
Yep.
When you refer to time, what is the scale of time?
Oh, it's a good question. So the scale here is just individual samples that are coming in.
Yeah. Okay.
So for example, if you have a 1 megahertz signal, you're sampling 1 megasample a second,
Okay.
then that's the rate. So the actually one way to figure it out is the size of, or the length of this plateau is the same as the length of the cyclic prefix. So if you have a 16 sample cyclic prefix, then this is 16 samples long. So you do your fine frequency offset correction. After you do your fine frequency offset correction, you have something that looks like this. So if you've ever done Fourier analysis using MATLAB or C++, you'll know that your spectrum looks a little bit like this. You get your positive frequencies and your negative frequencies. So instead of having a nice OFDM shape, it gets split up a little bit like this. Something you'll notice about this is, hang on, we've got an integer frequency offset. So this is our DC carrier, and that should be at 0. So the first step after your fine frequency correction is your integer frequency offset estimation. You can do that with a simple correlation. You get a nice clean peak telling you how many bins you're out by. You can rotate your spectrum in the frequency domain, and then you get what you want to see. You've got your DC carrier down at index 0. Looking at the scatter plot of the data coming through, you can see, hang on, we've still got a linear phase shift. We'll correct for that down the line. So we've now figured out where our frame is. We've pulled out our preamble, so we know what that looks like. We know what the preamble we transmitted was. We divided 2. It gives us an equalizer. So if you look at this particular equalizer here, it'll tell you a couple of things. It'll tell you that you've got some filter roll-off, so you see that's increasing towards the edges. That means that the original had some filter roll-off, so we're boosting that up again. And then you've got this interesting linear phase shift. So the scatter plot I showed you had that rotation that was caused by the linear phase shift. You can see it quite clearly here. So that's going to be corrected by our equalizer. And one of the interesting things about OFDM is that if you've got that linear phase shift in the frequency domain across the bins, that corresponds directly to a timing error. So in the time domain, if you're off by a certain number of samples, in the frequency domain, that looks like a linear phase shift across frequencies. And vice versa, actually, you've got a duality there. So if you look at, if we pull out the next symbol before we fully equalize it, you'll see that that linear phase shift exists through it. So our scatter plot looks a bit like this. You're not going to be able to pull out any data from that. So after we equalize it, it gets rid of that linear phase shift, starts to look like something we recognize. So you can see our real values up here are +1 or -1. Our phase values are small, pretty much 0. Anybody know what modulation type this is? No, this is just PPSK. So PPSK, you're modulating on the real axis, you're not modulating on the imaginary axis. So if you look at the individual symbols, you can see, okay, PPSK has these 2 points. As we move through the OFDM symbols in our frame, we can see that there's a fixed rotation in each one. We can correct for that by using our pilots. So each symbol has a number of pilot values, which we know the value of. We can use those to correct them. And we can pull out our BPSK points, and that's how we extract our data. So that's pretty much it. Having looked at OFDM, I want to talk a little bit about some interesting applications that came up recently in the past year. Has anybody heard of the DARPA Spectrum Challenge? Yes. Has anybody taken part in the DARPA Spectrum Challenge? No. So this is very interesting. DARPA is the Defense Advanced Research Projects Agency in the US. And they said they'd come up with this Spectrum Challenge, a competition to demonstrate a radio protocol that can best use a given communication channel in the presence of other dynamic users and interfering signals. So they decided that people would use a standardized radio hardware platform, so the USERP NG10 was decided on. And they ran head-to-head competitions where teams had to design a radio protocol that could operate in an environment with interference. So it was run in a structured testbed environment. This is run on the Orbit testbed in Rutgers. I don't know if many of you have used that already. In the same way it uses OMF, so it's quite similar to using the testbed here in Ghent. And the best strategies for guaranteeing successful communication in the presence of other competing radios will win, is the idea. So they had multiple phases. They had qualification, wildcard selection, and then they had 2 tournaments, competitive and cooperative. So the first, there were 2 phases as well. So the first phase was run just before Christmas, and the final phase will be run in March of this year. So for qualification, this was a step to get into the competition in the first place. You had to complete this. You had to design a radio for this scenario. So you've got a single radio pair, transmitter and receiver. You have to take input data from the source, packetize, transmit and receive. You're operating at 2.5 megahertz band. The score will be based on the total number of correct packets received in 5 minutes. And you have 3 types of possible interference. So you have a period with no interference. You have a 1-second period with short-term white noise in the lower half of that band, and then you've got a 1 second of interference that resides in the upper half of that band. And you don't know what sequence those types of interference are going to come in. So, given those parameters, what kind of radio would you design? Any ideas? So there's a couple of design choices. So just looking at those design choices, what would you go for? So would you go for simplex or duplex? Well, there isn't really any need for duplex. So it's just straight through, unless you're going to try and respond. So you could observe the environment at the receiver, tell your transmitter what's going on, and have the transmitter reconfigure. But that's an awful lot of back and forth when you're not going to achieve increased throughput. So you can choose whether you're going to use a robust waveform or whether you're going to detect and reconfigure. So any ideas? A room full of engineers has no ideas.